Hey guys, so I just wanted to record some of the walkthroughs for chapter 8, like we would normally do on the board, but alas, we're online now, so let's just jump straight into it. I am on number 10 in homework 8.1. So they tell us that most adults would erase all their personal information online if they could. A software firm survey of 560 randomly selected adults showed that 55% of them would erase all their personal information online if they could. And they want us to find the value of the test statistic. So you guys should have already seen, I posted a cheat sheet on when to use which equation. So if we pull out the information we have, we're looking for proportion. So the only formula that we use for a proportion is our z is equal to our p hat minus our p divided by the square root of p times q over n. So before we can solve this problem, we obviously have to find all of our variables. So for p hat, it's going to be our percentage that's given. So if you see in the problem, they say that it showed that 55% of them would erase their data. So our p hat would just be our 0.55, or our percentage as a decimal. And then q hat has the same relationship as p and q. So it would just be 1 minus 0.55, which is equal to 0.45. Our p is what kind of makes this tricky. So if you notice, they didn't actually give you a proportion, but when you look at the problem, they say that most adults. So whenever you see most, you know you're going to have more than 50% of people. So we just use 50% as our threshold. So our probability proportion will be 0.50 for 50%, which is most people would be more than 50. And then q would just be 1 minus 0.50, which is equal to also 0.50. It's a 50-50. And they say a software firm surveyed 560 people. So our n would be equal to 560. So once we have all of that, we can plug into our equation. So 0.55 minus our p, which is 0.50, divided by the square root of p times q, so 0.5 times 0.5 divided by n, which is 560. So once you calculate that out, it should be equal to our z-score, which is 2.3664. But if we round about, since we have to round to 2 decimal places, 2.37. And that's it for this problem. That is where we get this answer. So moving on to the next one, we're going to be looking at a problem looking at the mean instead of the proportion. So they tell us that the mean pulse rate in beats per minute of adult males is equal to 69 beats per minute. For a random sample of 170 adult males, the mean pulse rate is 68.2 beats per minute, and the standard deviation is 11.4. So if you remember from the cheat sheet, there are 2 options when you're dealing with the mean. You could be looking for the z-score or you could be looking for the t-score. So remember, you're using your z-score anytime you know sigma or your population standard deviation. And if you don't, then you're going to be looking to use t. So if we look at our problem, we were not given our population standard deviation. So we're going to write down what we do know. So we were given our sample mean, which was 68.2. We were given our population mean, which is our mu, 69. We're given our sample standard deviation of 11.4. And we were given our n for a total number of people, which was 170 adult males. So our formula for our t-score, actually I'm going to move this up a little higher just so I have more room. Our formula is x bar minus mu, so your sample mean divided by your population mean, or minus your population mean, divided by your sample standard deviation, or S, divided by square root of n. So as always, remember that you might want to do this calculation first because you want to make sure you're only dividing your sample standard deviation by the square root of your mean. You want to make sure it isn't connected to the rest of your problem. So that's just a side note, but for now we can plug in. Our t is equal to our x bar, which is the 68.2, minus our population mean of 69, all divided by, I'll even put it in parentheses just so we remember it's separate, our s, which is 11.4, divided by the square root of our n, which is 170. And again, the parentheses are just so you remember to do that portion by its lonesome. So when you calculate that portion out, we should get a t-score of negative 0.91, which is how we get this answer. So moving on to our next one, we did one for proportion, one for the mean. Now we're going to do one for the standard deviation. So our claim is that the standard deviation of pulse rates of adult males is more than 11 beats per minute. So we want to find, for a random sample of 155 adult males, the pulse rates have a standard deviation of 11.3. And then they tell us to find our test statistic. So our formula for our standard deviation is our chi-square is equal to n minus 1 times our sample standard deviation squared over our sigma squared, or our population standard deviation. So if we pull out what we know from the problem, we had our n, or our total population, equal to 155. We have our S, or our sample standard deviation, equal to 11.3. And we had our sigma, or our population standard deviation, equal to 11 flat. So if we plugged into our equation, our n minus 1 would have 155 minus 1 times our sample standard deviation, which is 11.3, squared, don't forget the square, divided by our sigma squared, also squared. Please don't forget those. So for my chi-square example, I end up with a chi-square value of 162.51, which is how I get this number. All right, so moving to the next problem, number 13, they tell you that the test statistic of z equals 0.78 is obtained when testing a claim that P is greater than 0.5. They want us to identify the hypothesis test as being either two-tailed, left-tailed, or right-tailed. And they want us to find the p-value, and then using your significance level, should we reject the null hypothesis or should we fail to reject it? So I want to go over this one because it has a lot of the key points in chapter 8. And also, hopefully if this comes up, I wanted to take a second to point out part of the slides for this section. So this is one of the slides from all of chapter 8. It's just something that's very important. So you want to be sure to recognize the difference between your p-value, your p, and your p-hat. So your p-value is the probability of a test statistic at least as extreme as the one obtained. So it's going directly off of your test statistic, whereas your p is your population proportion and your p-hat is your sample proportion. So think of p as your population, p-hat as your sample, and p-value is a representation of your test statistic. So moving that back over, they tell us that our test statistic is z equals 0.78, and we're testing the claim that p is greater than 0.5. So first thing we want to do is figure out if it is right-tailed, left-tailed, or two-tailed. So as part of the cheat sheet down towards the bottom, I did note this already, but if you're ever unsure of which one it would be, we have our not equals, which would be our two-tailed. And then the other two get tricky, but there's a good way to remember which one is which. So depending on which way it's pointing. So if you have a greater than, it's pointing towards the right. So it would be right-tailed. And then same works with less than. And because it points, even though I just wrote an arrow the other way, it's pointing towards the left. So it would be left-tailed. So if you're ever unsure of which way it's going, just go off of which way this is pointing. If it's pointing towards the left, then you want to think about it as left-tailed. And if it's pointing towards the right, you want to think about it as right-tailed. And that's also at the bottom of your cheat sheet. So if you're ever unsure, that's a good way to tell. So, all right, so we know this one is right-tailed because we have our p is greater than, and it is pointing towards the right. So that part's okay. So we can move on to our p-value. So when we're looking at our p-value, we can draw a graph actually, like we normally do. And we can think about our claim. So if we're looking at our p being greater than 0.5, if anything is greater than, it's going to be on this side of our graph or our bell curve. So we're going to be looking in this portion for our p-value. So if we know our z-score, I'll write it over here, our z is 0.78, we can go find our z-score. And remember that our area is given to the left, so we'll have to do 1 minus the z-score we're given. So, I erased it. So our z is equal to 0.78. So if we went and looked at a z-score table and went from 0.7 all the way to 0.8, we would get our z-score of 0.7823. So going back to our problem, remember that when we had our graph that I drew much better the first time, we were looking at this side. And remember that the Z table is always giving you the cumulative area to the left. So because we found the area on this side, we'll have to subtract by 1 to get our p-value area on this side. So we can just do 1 minus 0.7823, which will equal 0.218. Well, actually, that's going to be our final answer. So when we subtract, we'll get 2177. Just move back to a white screen so you guys can read it, which when we round will give us 0.218 because we're rounding to 3 decimal places. That's why I started to round early. All right, so that brings us to the last portion, which is choosing whether or not to reject our null hypothesis. So if we're looking at our hypotheses, we would have our H sub 0, or our null hypothesis, as our proportion being equal to 0.5, and then our alternative as our p is greater than 0.5. So whenever you're trying to figure out whether to reject or fail to reject, I also left a note on the cheat sheet. So if your p-value is less than or equal to your alpha, which your alpha is given up here with your significance, if your p-value is less than or equal to your alpha, you want to reject your null hypothesis. But if your p-value is greater than your alpha, you want to fail to reject your null hypothesis. So if we're looking at our p-value for this problem was 0.218, and our alpha, they told us was 0.01. So clearly our p-value is greater than our alpha. And when our p-value is greater than our alpha, we fail to reject. All right, so if we failed to reject, it would mean that there is no sufficient evidence to support the claim that our p is greater than 0.5.